One area where quantum communication over a quantum internet has shown great promise is to solve problems in distributed systems. So what does that mean? An important problem in computing is to coordinate between different computers, different processors. For example, to keep data in sync. If you store data in the cloud, like on Dropbox or Google Drive, you would like it to be the same everywhere, even if some of these computers go down or fail or behave erratically. Similarly, we might want to coordinate access to resources in the network. If I have very many computers and they all want the same resource, for example, they all want to use the printer or they all want to use a shared hard drive, it is important to coordinate access to that resource. Not everyone can access the resource at the same time, because then chaos would ensue and things would go wrong. Another example occurs when you imagine that, for example, we deploy some sensors, or if you want, little robots, on a mountain. Let's say we throw a number of these robots on the mountain, and some things might go wrong. Some of these robots might land in a puddle, others might die on impact, but nevertheless, we want to coordinate the actions of these robots or sensors on the mountain. And we want this to work even if some of them are working incorrectly. This is an area called distributed systems in classical computer science. And people have spent a lot of time exploring protocols that can coordinate between different processors, even if these processors are behaving erratically. In daily life, you never really experience these problems directly. But you would certainly notice their absence, because things would start to go wrong left and right. Now, the problem about computers that fail is, of course, that we may not always notice their failure. Maybe, for example, when we throw the robots on the mountain, they're not completely dead, but their memory might be corrupted. And whenever the robot wants to send a 0, it is actually sending a 1. So it is very difficult to find out, in fact, whether computers are behaving correctly on a network. But nevertheless, we want to coordinate. Some standard problems that people have studied in distributed systems, for example, is the task of leader election. There, one can imagine that all the robots on the mountain want to elect a leader, and the leader gets first access to a particular resource. One might also want to solve an agreement problem. If you think about the robots and the mountain, a very famous problem is the problem of Byzantine Agreement. Let's imagine we want to achieve agreement between these robots. For example, we want all the robots that are working correctly to walk in the same direction. So they should be walking either left or right, but it shouldn't be that half of them walk to the left and the other half walk to the right. A very famous version of this problem is called the Byzantine Generals problems, where you can imagine that these little robots on the hills that we've just deployed them on are pondering on attacking an army in the valley. Now, each of these robots can be behaving correctly or incorrectly. And it is not known to the other robots which ones are behaving correctly and which ones are faulty. In fact, some of these robots, in this particular situation, are maybe secretly controlled by the army in the valley, and they are traitors. Now, the robots can only talk to each other by sending messages, for example, over radio. And the coordination that they want to achieve is that they want to agree, for example, on a bit, 0 or 1. Say 0 for attack the army in the valley and 1 for retreat. Now, it is very important to the robots that they agree, because if only some of them decide to attack, and there's too few of them to defeat the army in the valley, they will get defeated. So we want that all the correctly functioning robots arrive at the same conclusion, to either attack or to retreat. Now the goal of designing a protocol for Byzantine Agreement is to come up with a protocol, namely a series of messages that the robots will exchange with each other in order to solve this problem. And our protocol should work if not too many of the robots are broken. So what does this word too many mean? So we want that the protocol works if, for example, less than a third of the robots are broken. Where does this funny number, a third, come from? It is easy to see that there's some limits to what we can hope to achieve here. Because if we only have 3 robots, let's say I'm robot number 1, then if my communication with the other 2 robots, say from interacting with robot number 2, I might conclude to attack, and from the messages from robot number 3, I might conclude retreat. So I'm not quite sure who to believe. So certainly, there are some limits of how many of these robots can be behaving incorrectly for us to form an agreement. So typically, one imposes some limits, like a third. So where does quantum communication come into this picture? Now you may be wondering, how long does it take these robots to arrive at an agreement? In particular, how many rounds of communication do they have to engage in, and therefore how much time does it take them in order to agree whether they're going to attack or retreat? Now it turns out there exist quantum protocols that can solve such tasks with a constant number of qubit rounds of communication, so a number of rounds that does not depend on how many robots there are on the mountain. Whereas classically, we need a number of rounds of communication that scales with the number of robots. So the more robots there are, the longer it takes. In fact, depending on the exact model, it can be logarithmically or the square root of the number of robots. So quantum communication has shown great potential in this domain, and researchers are actively working on trying to exploit this feature of entanglement to achieve maximum coordination to solve such agreement problems more efficiently.